everybody, how are you? Today I would like to talk about a topic in physics which causes trouble to many students when they first see it. So the students who take the physics class the first time, they study kinematics. They of course learn vectors and scalars, and then they start studying kinematics. In the kinematics chapter they mostly deal with one-dimensional systems. So the system's moving on a line, right? A system, a box, let's say, it's moving to the right, to the left, right? So there's an acceleration, okay? And you simply analyze the system moving on a line. In projectile motion, it's a two-dimensional motion. However, it is still the composition of two 1D motions. So it is a little bit an improvement to the 1D system, but it's not like a system rotating, right? So when the students first see the rotation concept or a circular motion concept, they get lost most of the time. So today I would like to introduce the circular motion by defining the quantities, physical quantities we use and their meanings, and then I'll drive some of the relations. Hi everybody, this is Arif. Today we will talk about circular motion, and I know that some of you have troubles with the concept of circular motion. So today I'll try to explain the details of the circular motion in physics, and I'll introduce the basic concepts. I'll introduce you the definitions we use in circular motion. We will talk about uniform circular motion and the generic circular motion, and I hope everything is going to be clear today. Circular motion is really important because it forms the basis for all the rotation stuff. So rotational kinematics, rotational dynamics, torque, angular momentum, so on and so forth. So if you do not understand the circular motion concept, all these topics would be really hard to understand. Okay, so if we say circular motion, what do we really mean? So what kind of a motion can be considered as a circular motion? For example, I have a pendulum. This point is fixed, the top point is fixed, and it's just moving like that. Is this a circular motion? Some say yes, some say no, right? Well, it is actually a circular motion because all the points on this rod are actually following circular trajectories. So if you have a system which is following a circular trajectory, the system is considered as going under a circular motion. So you do not have to complete the whole circle, okay, to name it as circular motion. So in a system which is following a trajectory of a circular arc is considered as going under a circular motion. So let's look at a typical system. So I'll draw a circle, okay. I have a point A. So let's suppose my system is at point A and it moves from A to B on this arc, circular arc. So at point A, it is moving in that direction. So we call this velocity as V tangential A. So as the system moves on this circle, right, the velocity is always tangent to the circle, right? So that's why we call it V tangential. So the velocity at point A is defined as V tangential A. And at point B, it's going to be also tangential, V tangential B. So these are vectors, right? So here is the center of my circle. So as I move from A to B, there is a change in the angle here, right? Let's call it delta theta. So what is the distance I traveled, right? It is nothing but this circular arc, right? So let's call it delta L. So what is delta L? Let's write it down. So delta L is simply equal to R times delta theta. So the linear distance, or the distance traveled on this circular arc, is simply equal to R times delta theta. Well, when this delta theta is equal to 2 pi, right, this is nothing but the circumference, right? That doesn't have to be 2 pi. It's just delta theta. Okay, so now if I ask you, what is the average speed as I move from A to B? What is the average speed? Okay, so if I call this V average, now this is a scalar quantity, right? So I just need to know the total distance traveled, which is this delta L here. R times delta theta over delta T. So what is delta T? The time it takes to go from A. So let's call it TA is equal to TA is equal to 0. And let's call TB is equal to delta T. So when time t is equal to 0, I'm at point A. When time t is equal to TB, which is delta T, I'm at point B. So this is my average speed as I move from A to B. However, let's look at this term, delta theta over delta T. It seems like a measure of how fast theta changes. So I simply call it angular speed. Okay? So omega average is defined as delta theta over delta T. So this is an angular quantity which is called angular speed. So the linear speed is related to the angular speed through this relation. So when delta T goes to 0, what happens? Okay, these average quantities turn into instantaneous, right? So I can simply say that V tangential is simply equal to R times d theta over dt, or you can simply call it R times omega. So if you want to use instantaneous quantities here, you simply take the derivative. Okay? D theta over dt is my omega at any given time t, which is the angular speed. So if I want to know, for example, the tangential speed at point A, what I need to do is, this is R times d theta over dt. I need to calculate this derivative at t is equal to 0. Because I know that when t is equal to 0, I'm at point A. This is simply what you do. The next part is, this tangential speed may not be constant. So as you're moving on the circular trajectory, you may be speeding up or you may be slowing down. So this tangential speed may be changing. Okay? So at that point, we now define acceleration, tangential acceleration, which will be equal to the time rate of change of the tangential speed. So you may have an acceleration which is tangent to the circle, right? So if A is in the same direction as Vt, you are speeding up. If A is in the opposite direction, you are slowing down, which is good. So this is equal to R times d omega over dt. And we call it alpha. So alpha is called the angular acceleration, time rate of change of omega. As you see, this is really interesting. We have a linear quantity, distance traveled. We have an angular quantity, change in angle. So we have tangential speed, we have angular speed. And we have tangential acceleration, we have angular acceleration. And the proportionality constant is the radius of the circle. And this is how the linear quantities are related to the angular quantities. So the next step is to discuss the uniform circular motion. Sometimes students say that, well, it is a type of circular motion, which is correct, okay, with constant velocity. Is it really true? Let's see that. So I'm drawing a circle. Okay. Let's pick a point on this circle. Let's pick this point A. And let's suppose this is point B. Let's show the velocity vectors at point A and point B. So the velocity is going to be tangent, right? VTA is like that. V tangential at point B is like that. Can we really have a circular motion with constant velocity? No. Okay? Even if they have the same magnitude, these two vectors are pointing different directions. So if we have constant velocity, it is a vector. It should have the same magnitude and it should point in the same direction at all times. So here what we see is these two velocities cannot be the same, even if their magnitudes are the same. This is how we define the uniform, constant speed. Okay? This is a circular motion with constant speed. So the magnitude of these velocities at any given point, they will be the same. So if this is a uniform circular motion, we know that at point A, V tangential A magnitude must be equal to V tangential B magnitude. So for simplicity, let's call it V tangential. So let's suppose we pick these points symmetric. In other words, if this is my vertical, this angle is theta, this angle is also theta. Let's draw our coordinate system. So this is my vertical, this is my horizontal. This is my vertical here. So let's call this y, this is x, this is of course y, and this is x. Now the question is, do we have acceleration? Yes, velocity is changing, right? So time rate of change of velocity is acceleration. So even if the speed doesn't change, we have to have some sort of an acceleration because velocity changes. So now our goal is to find the acceleration in this system. So in order to do that, we need to find the components of these velocities. That's why I drew y and x coordinate system. If this angle is theta, let's do it fast. So this angle is also theta, right? And this angle is also theta. Let's define another angle. So this is theta, this is 90 degrees, so let's call it alpha. So the radius vector and the tangential velocity, they are perpendicular to each other. And alpha plus theta is 90 degrees. So if this angle is alpha, this angle has to be theta. So we found this angle theta. So similarly, this angle would be alpha here, right? And this vector and this vector has to be perpendicular to each other. So this angle is also alpha. So this is the y-axis vertical, this is x-axis horizontal. They have to be perpendicular to each other. So this angle is also theta. This is very good. So let's find the components of VTA and VTB. VTAx is nothing but VT cosine theta, right? So what is VTBx? So this is also equal to VT cosine theta. Cosine theta and cosine theta. So what do we see here? There is actually no change in the x components of the velocity. So this result simply suggests that the x component of the acceleration must be equal to 0. This is very good. So let's see VTA y. The y component of VTA, which is going to be VT sine theta. So what is VTBy? It's going to be minus, right? It's pointing in the negative y direction. So minus VT sine theta. So definitely we have some change in the y components, right? A sub y must be equal to delta Vy over delta t. And this A sub y cannot be 0. Okay? So let's find what it is. So A sub y is simply equal to change in velocity. So final minus initial. This gives me minus 2 Vt sine theta divided by delta t. So what is delta t? So it is the time it takes to go from A to B. So I know the arc length here, which is r. So this is r times 2 theta, right? Divided by the speed. The speed is constant, V tangential. That's it. So A sub y, the y component of the acceleration, by the way, this is the average acceleration, is simply equal to minus Vt square over r sine theta over theta. The next question is, what happens if I take this theta go to 0, right? So in other words, we're going to make this A and B move towards each other. So let's take this point C. So when we take the limit, theta goes to 0, okay? This actually gives us the instantaneous acceleration at point C, okay? Because these points A and B get close to each other when theta goes to 0. Okay, so let's do it here. Limit theta goes to 0. We know that sine theta over theta is equal to 1. So this is one of the limits we know from calculus. So here when we take this limit, it becomes just 1. So the acceleration at point C is simply equal to minus v tangential square over r y hat. Because this is the y component, right? This is called the centripetal acceleration. At point C, we have an acceleration vector which is pointing towards the center of the circle. The center is here. And this acceleration is called the centripetal acceleration. Point C is not special. Any point on the circle is equally important, right? So if we picked any point here, let's say point D here. So if we had picked a point D here, so at this point what will happen is, this is my radius vector, so the acceleration would point simply towards the center. So this is the centripetal acceleration at point D. This is the centripetal acceleration at point C. So this would also have the value minus Vt square over r. Let's ask, why do we have acceleration here? Because the velocity changes. Its direction changes. Its magnitude doesn't change, but doesn't matter. Its direction changes. So when we have uniform circular motion, the direction of velocity changes. That's why we have this acceleration. One thing that we notice here is that this acceleration is perpendicular to the direction of motion. So at point C, I have a tangential velocity like that, V tangential C. And this acceleration is also perpendicular to the direction of motion. Okay, so the acceleration, which is perpendicular to the direction of motion, is responsible for changing the direction of motion, right? So this is a typical case we see in uniform circular motion. Acceleration is always perpendicular to the direction of motion, and it's responsible for changing the direction. So this acceleration has no effect in changing the magnitude of the velocity. Okay? In other words, in the tangential direction, we do not have any acceleration. So nothing is speeding it up or slowing it down. Vt doesn't change. Okay? So it was a sub t, right? So if we had the tangential acceleration, okay, the speed also changes. But in uniform circular motion, the only acceleration we have is perpendicular to the direction of motion. Okay, in the most general case then, so if you look at the most general case, we may both have a centripetal acceleration and a tangential acceleration. So in that case, we are not only moving on a circular trajectory, but we may be speeding up or we may be slowing down. So the speed is not constant, okay? So in the most general case, if we are moving on a circular trajectory like that, at any given time t, let's suppose I'm at point A, I will have a tangential velocity, okay, just like that. Okay, since you are moving on a circular trajectory, centripetal acceleration pointing towards the center of the circle. Okay, suppose the origin is here. And if we are speeding up, okay, let's assume we are speeding up, we will also have an acceleration, the component of an acceleration, which we call it a tangential. So in this case, the magnitude of velocity also changes, right? So if they ask us what is the net acceleration here, so we simply add these two vectors, right? But vectorially. So these are just like that. So you can simply say this is the net acceleration at point A. Okay. I hope this clarifies the circular motion topic. First, we defined the angular quantities and we showed their relation to the linear quantities, and then we discussed uniform circular motion, and we actually showed why we need to have an acceleration, okay, in uniform circular motion, even if the speed is constant. In the last step, we looked at the most general case where we have a centripetal acceleration and a tangential acceleration. This is all I want to talk about today. I hope you enjoyed it. See you next time. Take care. Bye.